Okay, so today we are going to talk about your energy changes. Okay, so some schools will brand this chapter as chemical energetics, but they mean the same thing. So the main idea in this chapter is to learn about your exothermic and your endothermic reactions, and then you'll talk about your overall energy change, and then you'll explain what does this actually really mean. So if you look at your first part, we're going to talk about your exothermic reactions. Okay, so when it comes to exothermic reactions, you can actually view this reaction as anything that causes your temperature of your surrounding to become hot. Okay, so basically it's a hot reaction in nature. Again, so over here for you to feel hot, okay, you must release energy, right, to your surroundings. Okay, so if you were to release energy to your surroundings, you'll realize that your reactant's energy level and your product's energy level will be a little bit different. So if you focus on the axis here, this is your energy axis, right, and this is your time axis. So because you have given out heat, right, it makes sense that your reactant's energy level will actually fall, right, and then your product's energy level will be lower. So now just for a very quick concept, okay, in terms of energy, right, who do you think is more stable? Do you think it's the reactants or do you think it's the products? Okay, so actually it will be the products that will actually be at a more stable level. So the reason why is because having less energy actually means that something will be more stable, right? So imagine if you have a kid, right, that is ADHD, right, compared to a kid, right, that is very chill, right, and he's always reading his books, right, compared to a kid that's jumping around, right. The one that's more stable is the one reading the book. Okay, the one who has a little bit less energy, not as active. Okay, so over here, take a look at your reactants and products. Okay, you will notice that there's a negative change. Okay, the energy change is downwards, right? So it's a negative change. Okay, so that's why we describe your energy change here to be negative. Okay, there's one more arrow that is not drawn inside this diagram. So I want you guys to draw it in. Okay, it's actually your arrow here, which represents your activation energy. Okay, so just one tip I want you guys to understand here is that the arrows will never be double-sided. It will always be single-sided, right? So it will be pointing towards your endpoint. Okay, always pointing towards your endpoint. Okay, so for example, so if for you guys who do not understand what is EA, right, we use this symbol to represent activation energy. Okay, so this is the energy that you need to kickstart a reaction. Okay, so what kind of reactions are exothermic in nature? So nearly all the reactions that you know, so acidic reactions, right, combustion, right, respiration, and anything that naturally forms bonds, right, all these are exothermic in nature. So if you're okay with that, let's move on to the next part. Let's talk about endothermic reactions. Okay, so endothermic reactions are reactions that actually help to absorb heat. Okay, they absorb more heat. Okay, so because of that, you will have a cooling effect in the surrounding. Okay, so if you take a look at the same axis of your energy against your progress, you realize because you have absorbed energy, your product will be at a higher energy level. Okay, so what are the arrows that we are missing? So first, we have your energy change arrow, right? So this, you will realize, will be a positive number. Okay, so we will write it here. The energy change is a positive number. Okay, other than that, you are missing your activation energy. So this is your EA. Alright, so if you have no questions, that is the main idea. So what are some examples of endothermic reactions? Okay, so the first and most important one is actually photosynthesis. So I need you to remember that. And the next one, right, is the dissolving. Right, so when I say dissolving, right, actually I'm going to be a little bit more specific. We're going to talk about the dissolving of ammonium compounds. Okay, so when you dissolve any ammonium related compound, it will actually create a cooling effect, and that's why it will be an endothermic reaction. Okay, so I need you guys to remember these two by heart. These two are frequently tested. Okay, so if you're okay with that, let me introduce you the formula. where it comes with energy changes. So energy change can be taken to be your E in minus E out. So what is E in? E in is the energy taken in to break bonds, and E out will be your energy given out to form bonds. Okay, so over here, it makes sense that when you take in energy, you will break bonds, right? So the opposite of that is when you form bonds, you must give out energy. Okay. So the next thing here is I need to go through covalent bonds with you. Right, so for example, I have H2O. I need you to be able to draw this out. Okay, if I give you N2, you need to be able to draw this out. O2 and CO2. So the idea here is for you to be able to understand what are the bonds present inside each covalent compound. Okay? So if you're okay with this, can you do me a favor and help me to try these 3 questions? Okay, so at this point in time, let the students draw out, then you will help them for the last one. Okay, right? If not, that is the main idea of this part. Okay, so now I'll resume. Okay, so very good. Now that you guys have drawn this, let me show you how do you use these drawings to help you to solve a question. Okay, so over here, you will have bond energy values. So this will be usually given to you already. Okay, so this will be the energy that you need to break a certain bond. Okay, so over here, if you look at the sample question, you have N2 plus 3H2 to give me 2NH3. Right, so what you want to do first, right, okay, because they ask you to calculate your enthalpy change, your energy change, you must first draw out the bonds. Okay, so in N2, H2, and in NH3. Okay, so now you will calculate your E in and your E out. So E in, you're going to break this and this. Okay, so key in the values. You will have 160, right, and 50. So you get about 310. Okay, and then for your E out, you will have 6 NH bonds. Okay, so over here, you will take 6 times of 300. Okay, so this will arrive at 1800. So you minus them off, you get minus 1490 kilojoule per mole. Okay, and because this number is a negative number, you will be able to understand and interpret that this reaction is a exothermic reaction. Okay, so once you guys are okay, let me get you guys to try some questions. Okay, so at this point in time, you can let the students try a couple of them. So page 10 is something to get them started off with. Then page 11 also. Alright, so if you feel like you need to give them more questions to practice, you can give them more at the later part. Okay, so just 10 and 11, make sure that they are able to do it. Okay? So once they are done, right, bring them to this page. Okay, so now, right, let's talk a little bit more about your energy change. Okay, so what does energy change really mean? Okay, so for example, right, you have this reaction, and let's say the energy change is minus 60. Okay, so that means, right, that if you have 1 mole of nitrogen, 3 moles of hydrogen to produce 2 moles of ammonia, it will release 60 kilojoules worth of energy. Okay, that's what they are telling you. However, if let's say instead of using 1 here, I will use 10 of it. Instead of 3, I use 10 times more, and instead of 2 of these, I produce 10 times more. It basically means that this reaction has occurred 10 times. So the total energy here, you must times 10 as well. You get the idea? Can I? So what am I trying to tell you here, right, is that this follows the mole ratio. Can? So to let you get a clearer understanding of this, let's take a look. What happens to your energy change if 30 grams of hydrogen was used instead? Okay, so the moles of hydrogen now, you will realize is 15. Originally, right, you used 3 moles to give you 60 kilojoules worth of energy. So from here to here is a 5-time multiplication. So you'll multiply 60 by 5 times, and then you'll get negative 300. Okay, so that is the idea behind this part. So if you're okay, let me just direct you to more questions to try. Okay, so I want you guys to try the question here on page 15. All right, and the question here on page page 14, 15, here, 15 and 16. Okay? So once you guys are done with that, okay, let me run through the last part with you guys. So now, right, just to do a very brief summary of everything that we have learned so far. Okay, we talked about endo and exothermic reactions today. So over here, I'm going to focus on how do you explain why is it an exo or why is it an endothermic reaction. Okay, so when you look at an exothermic reaction here, okay, there are three ways to explain why is this exothermic based on the graph. Okay, so first is the easiest way. So you can say that, oh, your energy change is negative and therefore it is exothermic. Okay, other than that, I want you to see something. Okay, because you know that your E in minus E out will give you your enthalpy change. Right, remember we take in energy to do bond break, right, and we give out energy to do bond forming. Okay, so if let's say, if your enthalpy change is going to be less than 0, then it means, right, that your bond forming is way more than your bond breaking. Okay, and that is why in the second part, we say that the energy given out to form bonds is more than the energy taken in to break bonds. Okay, the method 3, we hardly use it, right, but it's just basically telling you that the energy of the reactants, which is at a higher ground, is greater than that of the products at the bottom. Okay, right, but we're going to focus on number 1 and number 2 here. Okay, so same for endothermic reactions. Right, you can see this. Okay, when you see this method 1, you can tell me, oh, the enthalpy change is positive, so the reaction is considered to be endothermic. Okay, but same thing, right? If you were to write out delta H is equals to E in minus E out, and this is bond break minus bond form. If your delta H is going to be more than 0, then you'll realize that your bond break must be bigger. Okay, so your bond breaking is more than your bond forming. So finally, you can tell me that in method 2, your energy given out to form bonds will always be less than the energy taken into break bonds. Okay, so once you are done with this, you can actually direct the students to the rest of the questions, right? So you can get them to do this. Okay, this is on page 12. You can ask them to do page 13, right? Page 14. Right, basically you can finish up the rest also, right? 17 as well. Okay, so if not, then that is more or less the end of this lesson.